All right, let's jump right into a really cool number puzzle. Now, this one might look a little tricky at first, but trust me, it's all about spotting a hidden pattern. I'm going to walk you through it, so let's get started. So, what's the big mystery here? Well, it turns out some numbers have this special property. Think of it like a secret code. Our job, it's to crack that code and find all the numbers that have it. Okay, so here's the official challenge laid out for us. We need to find all the natural numbers below 50, where the number itself is the sum of 3 of its own distinct factors. Sounds like a mouthful, right? Don't worry, let's break that down. First things first, what's a natural number? Super simple. It's just your basic counting numbers. 1, 2, 3, 4, and so on. Pretty straightforward, right? And for this problem, we only care about the ones under 50. And the other key term is factor. So what's a factor? It's just any number that divides another number perfectly, with no remainder. Take the number 6, for example. Its factors are 1, 2, 3, and 6, because they all go into 6 nice and clean. Okay, now that we've got the lingo down, let the investigation begin. With a puzzle like this, the best way to crack it isn't to go looking for some complicated formula. Nope. You start small. You look for clues. So, let's put on our detective hats and open up our very first case file. And our first subject is the number 6. It's a nice, small, manageable number, the perfect place to start digging for some evidence. Okay, so the factors of 6 are 1, 2, 3, and 6. The mission, remember, is to find 3 different factors from this list that add up to 6. And would you look at that? 1 plus 2 plus 3, that equals 6. Perfect. We've got our first success. So the number 6 definitely has this secret property. Awesome. Now let's see if we can find another one. All right, let's open up the next case file, the number 12. Does this one fit the profile? Let's find out. So the factors of 12 are 1, 2, 3, 4, 6, and 12. We've got a few more options to play with this time. Let's try mixing and matching a few of them. And bingo! 2 plus 4 plus 6, that adds up to 12. We found another one. Okay, now this is getting interesting. I think we might be onto something here. And actually, if you keep going, you'll find that 18 works, and so does 24. Just look at this summary we've got. For 6, the factors were 1, 2, 3. For 12, it was 2, 4, 6. For 18, we got 3, 6, 9. And for 24, it's 4, 8, 12. You seeing it? A pattern is definitely starting to emerge. Okay, this is the moment we've been waiting for. We've gathered all the clues. Now, it's time to connect the dots and finally reveal the hidden rule that ties all these numbers together. Just take a second and look at those numbers and the factors that worked. Do you see the connection? How do those 3 factors relate back to the original number, n? This is the aha moment right here. Check out this relationship. For the number 12, the factors that work are 2, 4, and 6. Well, guess what? Those are just 12 divided by 6, 12 divided by 3, and 12 divided by 2. And it's the same for the number 6. The factors 1, 2, and 3 are just 6 divided by 6, 6 divided by 3, and 6 divided by 2. So there it is. That's the hidden pattern. The 3 special factors are always the number n divided by 2, n divided by 3, and n divided by 6. We've totally cracked the code. But wait a second. Is this the only pattern that could possibly work? A good detective always confirms their theory. So let's just do a quick check to make sure this is the one and only solution. And the proof is actually pretty simple. If we call those 3 special factors n divided by a, n divided by b, and n divided by c, then the whole equation simplifies way down to this. 1 equals 1 over a plus 1 over b plus 1 over c. And it just so happens that the only distinct whole numbers that make that equation true are 2, 3, and 6. So that confirms it. The factors have to be n divided by 2, n divided by 3, and n divided by 6. So here's the absolute key. For n divided by 2, n divided by 3, and n divided by 6 to actually be factors, they have to be whole numbers, right? And for that to happen, n has to be divisible by 2, and by 3, and by 6. Or to put it simply, n has to be a multiple of 6. And just like that, the whole mystery is solved. The problem just became super simple. All we have to do now is count up all the multiples of 6 that are less than 50. So let's just list them out. We've got 6, 12, 18, 24, 30,
36, 42, and 48. Every single one of those numbers follows our rule. And there you have it. That's the complete list.
Which means the final answer to our question, how many of these numbers are there below 50, is simply 8. There are exactly 8 of them. But just getting the right answer isn't the only point here. There's a much bigger takeaway about how we can approach all kinds of problems. And this quote kind of says it all. Success isn't always about just grinding through every single possibility. It's about taking a step back and spotting the hidden pattern. We didn't need to test all 49 numbers one by one. All we had to do was find that simple underlying rule. And that really leaves us with a final thought, doesn't it? This way of thinking, it goes way beyond just math puzzles. It really makes you wonder what other beautiful, simple patterns are just hiding out there in plain sight, waiting for us to find them.